Hey guys, welcome back to another video in the Digital Logic series. Today we're going to be looking at another problem from the textbook about constructing truth tables from a given expression. So the baseline tool for verifying your circuit logic before you start drawing gate diagrams is the truth table. So this is a complete map showing the output for every single possible combinations of inputs. And the main mechanics you're going to want to know for this problem is how the following operators work, and that is the AND operator, OR operator, and NOT operator. So when working with AND, you'll notice that the output is only 1 if all of the inputs are 1. And you'll know you're working with AND when you see two terms either directly next to each other or two variables, or you see two variables separated by a dot. The next one is the OR operator. This output is 1 if at least one of the other inputs is 1, and you'll know you're working with OR if you see the variables separated by this addition symbol. And finally, the NOT operator. This flips zeros to ones and ones to zeros, and you'll know you're working with that if you see a caret to the right of the variable or a solid line above it. If you're learning this topic or you're a beginner, I recommend writing down these truth tables on your paper for reference. If you don't, otherwise just go back in the video if you need a refresher for the following problems that we're about to start. Okay, so looking at problem A, we see that there are 3 variables. The first thing you're going to want to do when starting a problem like this is writing out all the possible combinations for these variables in a table. So I've gone ahead and done that, and you also want to add the letter F to the right of the variables to indicate the output. This is what we're solving for. So once you've done this, you're going to go through each case and fill out the truth table for the function F. And for the purpose of this tutorial, I'm going to go through each term. It's not necessary, but it's a great way to start, especially if you're learning the material and you're trying to become more confident. And once you've done this a couple times, you'll start to be able to do this in your head. Okay, so right away, we see row number 1. We see all the terms are 0. So this means we will plug in 0 for A, 0 for B, and 0 for C. And if you remember from the introduction, this caret is a NOT operator, and it will flip a 0 to a 1 and a 1 to a 0. Okay, so for the first term, we have 1 or 0. We know that this becomes 1. And from here we have 0 or 0. This becomes 0. Now in between here, we see that this is the multiplication. Two terms next to each other references an AND operator. So this will come out to 1 and 0, which we know is 0. I'm going to speed up the video from here and work through the rest of these. If you get stuck, just pause the video at any time. Okay, so after going through all the outputs, your final answer should be this column F. And we are finished with problem A. Okay, so for this next example, we could start right away by plugging in our test cases and going through every single input combination row by row, but there's actually a much simpler and faster way to handle this. Instead of trying to calculate the entire expression at once, we can solve for each product term individually in its own column, and then at the very end, because these terms are separated by logical OR operators, we know that the golden rule of the OR gate is at least one of the terms has to be 1 for the final output to be 1. So let's go through the table term by term, and before combining them for the instant final answer, we'll just map out the first column. So we see here the first term is AB. And then the second term here, this is A, B naught, C naught. And then finally our last term will be A naught, B, C. And then don't forget the F for the output of what we're solving for. So looking at the first column, we see AB. The only way this can be true, because it's an AND gate, is A and B must be 1. And if we look at the table here, we see A and B are 1 at that location. So this will be 0 for all rows except those bottom 2. Next, we move on to A and B naught and C naught. This will only be true when A is 1, B is 0, and C is 0. Because the B and C have the not operators, we know those zeros actually become 1. So what we'll be looking for is 1, 0, 0. And looking at the table, we see 1, 0, 0 here. So this will be 0 for all rows except that one. And now finally we have A naught, B and B and C. So we'll be looking for 0, 1, 1. And it'll be 0 for everything except that one row. Okay, now that we've done this, we know, again, that the function output will be 1 if at least one term is 1. So looking at the first row, we see we only have zeros, so the output will be 0. Same for the second and third row, but you'll notice in the fourth row, we see a 1 right here, so the output will be 1. The row after that, we see another 1, so the output will be 1. The row after that, there are 0, 1, so the output will be 0. And then for the bottom 2 rows, we see that there's a 1 here and a 1 here, so the output will be 1. And this leaves your final answer as this column F here. Okay, for the final problem here, there's actually a small trick we can use that will make our life a lot easier, and that's called the consensus theorem. Now, with the previous 2 problems, there actually were opportunities to simplify, but because the video is about truth tables, I didn't want to jump into any Boolean algebra. I'm going to leave that for a later video, but this trick is so simple, we might as well just include it now. If we look at the first 2 terms here, we see x naught and y, and x and z naught. The variable x appears inverted in the first term and normal in the second. If you take the remaining literals, which would be this y here and this z naught here, and multiply them together, you get y and z naught. And because that exact term appears here, this is called the consensus term, and it's already being added to the end of our expression, and it's redundant. So the logic of the first 2 terms already covers every state where y and z naught would be true, so we can drop it entirely. This means that the expression will now simplify to x naught and y, or x and z naught. And from here, we can follow the same process as we did for the previous problem, because these terms are separated by that logic OR operator, we just know that the rule is at least one term must be 1 for the final output to be 1. So we'll write in our new columns. We have x naught and y. And then we have x and z naught. For this, we're looking when x will be 0 and when y will be 1. We see that is right here, so it will be 0 everywhere else. And then for this one, we're looking for when x is 1 and z is 0. So that is 1 right here and 1 right here, and it will be z everywhere else. And now, since they're separated by that OR operator, we're just looking for when there is 1, 1. So here will be 0, 0. We see the 1 here, so this will be 1. And then we see a 1 here, so this will be 1, 1, 0, 1, 0. So this is your final answer. So that's all for this video on constructing truth tables. Thanks for watching, and if you have any questions on these examples or suggestions for specific problems that you want to see in the next video, just leave that in the comments below, and make sure to check out any other videos in the channel if you need any additional help. See you in the next one.